Suppose we have two random variables and we have complete information about their separate distributions. What can we say about the sum of the two random variables? Well, let's look at an example. Here are two random variables x and y. Each of them is a standard normal random variable. What's the law of x plus y? Well, it turns out that this is an ill-posed question. There's just no way to answer it because there isn't enough information. Let's look at two ways to model what's stated in this problem. First, suppose that x and y are equal. Then x and y are two random variables with the same distribution, standard normal in this case. Then x plus y is just 2x. What's the distribution of 2x? One quick way to understand that is to look at the cumulative distribution function, f of 2x at t, which is the probability that 2x is less than or equal to t, which is of course the same as the probability that x is less than or equal to t over 2. That is, it's the cumulative distribution function of x at t over 2. Now in this case we have a random variable with a density, and therefore that density, often denoted a little x, is the derivative of fx at t over 2, which is 1/2 the derivative fx, which is the density of x, at t over 2. We know the density of a standard normal, so this is 1/2 of 1 over root 2 pi, e to the minus 1/2 of t over 2 squared. In other words, it's 1 over root 8 pi, e to the minus t squared over 8. And that is the density of a standard normal of variance 4. So here we have that x plus y is equal in distribution to a standard normal of variance 4. Now, we knew it had to have variance 4, of course, because the variance of 2x is 2 squared times the variance of x. The fact that it's normal is interesting, and we'll come back to calculations like that later. So we would be tempted to say then the answer is it must be that x plus y has the distribution normal of mean 0 and variance 4. But that's just in the model where the two are equal. What about if I take x equal to minus y? Now, that's still two standard normals, because if y is a standard normal, then minus y is also a standard normal, and that's because the normal density is a symmetric function. And so if I do the same kind of calculation that I did over here, I will see that by plugging in minus t for t, I don't change the result. But in this case, x plus y is identically 0. So the law of x plus y in that model is a point mass at 0. So we see, since these two are not equal, that this question is just not well posed. In other words, the law of x plus y is just not determined by the laws of x and y separately. But it is determined by their joint law. We have to think of x and y together as a random vector. If we know the complete law of that random vector, then we will be able to determine the law of x plus y. The information of the joint law is much greater than the information of these separately. The standard terminology that's used is that these are the marginal laws of the joint law. The reason for that is pictorial. If I think in a discrete context of having two discrete random variables taking values in some finite set, then their joint distribution is this square with the values on the vertices. And to recover the individual distributions of x and y, we of course, using Tineli's theorem if you like, have to integrate out to get the values here and the values there in the margins. So how do we determine the law of x plus y knowing the joint distribution of x and y? Well, we can be even more general here and do this for sums of random vectors. So suppose x and y are two random vectors in Rd. Then the law of x plus y at a Borel set in Rd, we can write as usual by integrating that law over the Borel set B. And let's write what that is by definition. It's the full Lebesgue integral of the indicator function of B against that law. And now we're going to use the change of variables formula for this random variable, which says that that is the same thing as the expected value of this Borel function composed with the random variable x plus y. But x plus y is a Borel function of x and y together. F is the Borel function x plus y. And so we're going to use the change of variables theorem again, this time for the random vector xy, to write this as the integral now over r2d instead of rd of the function, indicator function of b composed with f at xy, integrated against the joint law of x and y. In other words, this is the integral over r2d of indicator of b at x plus y, integrated against that joint law. So that is how the joint law determines the law of x plus y. If we know this measure, then we can calculate this measure. Now that's about as much as we can say in this general context. But if x and y are independent random variables, which is the case we're going to be most interested in, then we have a complete description of their joint law. It's just the product measure. And so, following this formula, we can write that the law of x plus y on a Borel set is the r2d integral of the indicator function of b evaluated at x plus y against the product measure. And now let's go ahead and use Tineli's theorem and write that as the integral over rd of, let's say, the y law of the integral over rd of the x law, integrating that indicator function. In other words, if they're independent, we can calculate this as an iterated integral. Now we can think of this operation here, or here, as a function of two probability measures. We don't need the reference random variables around anymore. And so let's take that as a definition. Given any two Borel probability measures on, say, Rd, their convolution, mu star nu in notation, is the probability measure so defined. We integrate the indicator function of a Borel set B, evaluated at x plus y, against the product of mu and nu, which, as we just saw, can be written as an iterated integral in this order or the other one. Now let's simplify this a little bit. This indicator function here is equal to 1 if and only if x plus y is in B and 0 otherwise. So we can write that as being 1 if and only if x is in the translated Borel set b minus y. And so we can just rewrite this inside integral as the indicator function of that translated set, indicator of b minus y at x. But of course that inside integral can now be evaluated. And so what we're left with is the single integral over Rd of the function, the mu measure of the translated Borel set, b minus y, integrated against nu of dy. Now you might wonder whether there's any question about this being an integrable or even measurable function, but in fact we just proved that it is a measurable and integrable function thanks to this representation and Tineli's theorem. So this is the most general formula we can give for convolution in this setting. And as we saw by getting here, if I have two random variables that have these two measures as their distributions, then this convolution represents the distribution of the sum of the two independent random variables. And we can just observe from there that since the law of x plus y is the same as the law of y plus x, since x plus y equals y plus x, this convolution operation must be commutative. Now we can prove that directly right from here or here using Tineli's theorem, but it follows more easily just from this observation. Now, if we have a little bit of information about the measures, we can do better in finding a nice way to compute this convolution. For example, And these are the two principal examples that one sees in an undergraduate probability class. If both of the measures are absolutely continuous with respect to Lebesgue measure, in other words, if they have densities, or, on the other hand, if they are both discrete measures, pure point measures, then we can do better and give nice, elegant formulas for this convolution. So let's look here at the case where they have densities. Let's call the two densities f and g, which are then non-negative L1 functions. Then the convolution of mu and nu at a Borel set is using the first formula, this iterated integral of the indicator of b at x plus y. And now let's write down what mu and nu are, their integration against the densities f and g. Now here's what we're going to do. We're going to do a change of variables in the inside integral here. We're going to let x plus y be denoted as u. For the inside integral, x is just a parameter. We're integrating against y. And so y, therefore, can be rewritten as u minus x. And then the question is, how do we represent this dy integral as a du integral? Well, if this were a calculus class, we'd know how to do that. And in fact, it works exactly the same way, because we can just note that if I integrate an L1 function h translated by a against the Lebesgue measure, then that's equal to the integral of the function not translated against the Lebesgue measure. And that follows easily from the fact that the Lebesgue measure is translation invariant. One can take this and see immediately that this holds true for indicator functions, and then by linearity for simple functions, and then by the usual jazz for all measurable positive functions, and then for all L1 functions. So we will do our standard change of variables here, meaning that we can rewrite that inside integral as the indicator of b evaluated at u times g of u minus x integrated against du. Now I'm going to apply Tineli's theorem, everything inside is non-negative and measurable, to exchange the order of integration, and therefore write this as the integral of the indicator function of b against lambda of the integral of f at x g of u minus x against lambda of dx. If I give this inside function a name here, I'm going to call it f star g at u. Then this says that in order to calculate the measure of b with respect to the convolution here, I have to take this function and integrate it over b. So that's the integral over b of f star g d lambda. Notice that this function here is a non-negative function, because this product as a function of u is non-negative, given that f and g are. And moreover, we can easily check that if I take b equal to the whole sample space, that's the same thing from what we just computed as taking b equal to the whole sample space here. But the convolution of those two measures, which is the law of a random variable, is a probability measure, which means that the integral of this function over the whole sample space will be 1. So this is a probability density, and we have now identified the probability density of the convolution. So that is, the convolution of two absolutely continuous probability measures is an absolutely continuous probability measure, and its density is this f star g thing, which we call the convolution of the L1 densities. So we can calculate convolutions as integrals. In fact, we can do that in general if we know how to calculate integrals like this, but in the case where we have densities, we can do it as an integral that looks more familiar. Indeed, if these functions f and g are continuous, then this just becomes an improper Riemann integral. So that's the story on convolution of absolutely continuous measures. In the mirror universe, where we have pure point measures, we have actually a similar formula. So starting again with this representation of the convolution of two measures, we're going to go ahead and make the assumption, which we'll justify through the calculation, that the convolution of two discrete measures will be discrete, which means that it's totally determined by its value on singleton sets. So the convolution at the singleton set, the point u, is just the integral of this function, the new measure of the point u minus x, against mu of dx. Now mu is a discrete measure, so integrating against it is just doing a sum, which is at most countable, but as usual we write it as the sum over all x of nu of u minus x singleton mu of x. And actually this gives us enough information already to justify the claim that the convolution in this case is a discrete measure, because if I take this function of u and I sum it over all values of u, I can reverse the order of summation here using Tineli's theorem for counting a measure. That gives me the sum over x of mu of x times the sum over u of nu of u minus x. Now for the inside sum, as u ranges through the full real space, this translate u minus x for this fixed parameter x also ranges through the full real space, because subtracting x is a bijection of Rd. And so that means that the inside sum, by changing variables and calling u minus x v, which is, as we just noted, an arbitrary point in Rd, can be rewritten as the sum over all v of nu of v. But nu is a discrete probability measure, and so that is just 1, which means that this double sum is equal to just the sum of mu of x, which for the same reason is just equal to 1. And so we see that this function of u is a discrete function which sums up to 1. It is a discrete probability measure. And so there's no mass left over to assign to any non-singleton sets. This measure is indeed a discrete probability measure. This formula here is the discrete version of the convolution of densities formula we had on the last slide. This is the convolution of the probability mass functions. So let's do an example here. Suppose I have two random variables mu and nu that are both Poisson. Those are discrete random variables. The only values they can take are in the non-negative integers. I'll allow them to have different means, alpha and beta. Let's compute the convolution of those two Poisson measures. In other words, we're calculating the law of the sum of two independent Poisson random variables. So the convolution of these two measures gives the following mass to a number k. It's the sum, and we'll just be general for the moment and say over all real numbers x of mu of the singleton x times nu of the singleton k minus x. Now, of course, the terms in that sum are almost always 0. There's only a countable set where each of them is non-zero, and we have to see where they overlap. This one is 0 unless x is a natural number, 0, 1, 2, 3, 4, etc., since mu is a Poisson law. And the same here. This one is 0 unless k minus x is in the natural numbers. So what that tells us, putting them together, is that to get a non-zero contribution here, we need to have x in the set between 0 and k. Otherwise, we'll get 0. And so this is actually just a finite sum. It's the sum, j going from 0 up to k, of those point measures. So that's e to the minus alpha, alpha to the j over j factorial, times e to the minus beta, beta to the k minus j over k minus j factorial. And now we can factor out the e to the minus alpha and e to the minus beta, and we're left with a nice sum. And we should recognize that this looks like a binomial expansion. It almost is, but the coefficient in here is not a binomial coefficient. It's missing a k factorial. And so we'll put in and take out that k factorial. And now the terms inside the sum really are a binomial expansion which exactly gives us alpha plus beta to the k. And what we've seen here, therefore, since these are exactly the probability masses of a Poisson random variable of parameter alpha plus beta, is that the convolution of two Poisson measures is a Poisson measure with parameter the sum of the two parameters. That is, the sum of two independent Poisson random variables is a Poisson random variable whose mean is the sum of the two means. Of course, we knew its mean had to be the sum of the two means because regardless of whether two random variables are independent or not, the expectation of their sum is the sum of the expectations. Let's look at a continuous example. Suppose, like in the first slide, I have two normal random variables. That is, if I take two measures, mu and nu, which are actually both the standard normal law, meaning that they have this as their density, I'd like to compute their convolution. I'd like to know what is the law of a sum of two independent standard normal random variables. Well, now we use the formula for the convolution of two measures that have densities. So that's given here. This is an integral over the real line. And we have those densities, so let's just do some calculus. So the 1 over root 2 pi is combined to a 1 over 2 pi. Now on the inside here, I combine those into a single exponential of minus 1/2 x squared minus 1/2 u minus x quantity squared. We're integrating against x, so I'd like to simplify this as a function of x. So if I expand this out and then complete the square, which is what we'll need to do in order to simplify it appropriately, I find that inside the exponential what I have is negative x minus u over 2 squared minus 1/4 of u squared. And so that means that this convolution is 1 over 2 pi. That e to the minus 1/4 u squared can just come outside the integral with respect to x. And I have the integral of e to the minus x minus u over 2 squared dx. And now we do the same trick that we've done twice while computing these formulas for convolutions. And note that with respect to this x integral, u over 2 inside is a constant. And so we will do a change of variables, call this v, use the fact that dx equals dv, like we did before. Because we're integrating over the whole real line, that doesn't change the domain of integration. And this becomes 1 over 2 pi, e to the minus 1/4 u squared, the integral of e to the minus v squared dv. Now that's something that we did, albeit with a factor of 2 in there, and so we can use the same polar coordinate Tineli argument to compute that this is the square root of pi. And so at the end of the day, we get the following density. This is 1 over square root of 4 pi e to the minus u squared over 4, which is the density of a normal random variable of variance 2. Now, again, we knew that the variance had to turn out to be 2, because what we're computing here is the law of x plus y, where x and y are both standard normals and are independent. If they're independent, then they're uncorrelated, and therefore the variance of x plus y will equal the variance of x plus the variance of y, which is 1 plus 1, or 2. The more interesting feature here is that the convolution of two normals turned out to be a normal, just like the convolution of two Poissons turned out to be a Poisson. There are a few families of random variables like this that are closed under convolution. These two are the most important. And in fact, it's much more general with the Gaussians. An annoying generalization of this calculation that you should do once and only once in your life shows that if I have any two normals of any means and any variances, then their convolution is a normal random variable. And once you know that, you know what the parameters must be. The mean of the sum must be the sum of the means, and because they're independent, the variance of the sum must be the sum of the variances. So now we've had some practice with computing some convolutions, let's start to look at sums of more than two independent random variables. That's going to be one of our mainstays of study throughout this course, looking at the random variable Sn, which is the sum of n random variables in a sequence. Let's take those random variables in the sequence to be IID. Then how do I calculate the law of that sum? Well, if I note that that sum is Sn minus 1 plus xn, and by the grouping lemma, these two random variables are independent from each other, since all of the ones they're built from are independent from each other, then I can compute this as a convolution. This is the law of Sn minus 1 convolved with the law of xn. Okay, but how do I compute this one? Well, same way. And if I continue by induction, I'll get that this is the law of x1 convolved with the law of x2 convolved with, etc. down the line, eventually convolved with the law of xn. Now, do I really need all those brackets there? No, because addition is associative. And that means that since what this thing is just the law of this dude here, it doesn't matter what order I do the convolutions. Convolution is an associative and commutative operation. So, for example, taking advantage of the calculations that we just did, suppose that I have the law mu is a Poisson law of mean alpha. That is, I take n independent Poissons of the same parameter alpha. Then the law of their sum is going to be a Poisson whose mean is n times alpha. And just to remind you, that means that the mean of this random variable Sn is n times alpha, and for Poissons, the variance is the same as the mean. Okay, what if instead mu was a normal distribution? Let's take it to have mean 0, but an arbitrary variance, which we'll call s squared here. Then, again, by the calculation we just did, adding any two of them gives us a normal, and the variances add, so the law of the sum Sn is a normal of mean 0 and variance n s squared. That is, the mean is still 0, and the variance is n s squared. Okay, great. Now, as n is growing, we see that the mean, or at least the variance, is also exploding in these cases. So if we're interested in some kind of limit of these things, we're going to have to rescale them. What should we rescale them by? Thinking back several weeks when we introduced Chebyshev's inequality and did the weak law of large numbers, we may be inclined to divide by n. And if we divide by n, that's certainly going to take care of this, but what will it do to this? There might be different rescalings that we'll want to use in different situations. So let's be fairly general right now. Let's rescale by a parameter bn, a real number sequence that is probably going to tend to infinity in order to compensate for this blowup. Then we can just quickly calculate, of course, that the expected value of this renormalized sum by linearity is going to be n over bn times the expected value of any one of the terms in this IID sequence. So indeed, if we want to stabilize the mean, we should take bn to grow linearly with n. But what about the variance? So the variance of this renormalization, because it's a quadratic function, pulls a bn squared out. But again, the variance of a sum is the sum of the variances in this uncorrelated, because independent, setting. And so here I get n over bn squared. So what that tells us is that if we want to stabilize the variance, we should choose bn equal to the square root of n. So those two are inconsistent, but we'll see shortly, and you probably already know, how to do them together in series, so to speak. As a last calculation here to whet your appetite for what comes next, let's look at the normal case again and prove what I'll call an embryonic central limit theorem. I think it's too early in development to even call it a baby central limit theorem. Let xn be an IID sequence of normal random variables. Let's make them all centered, but they'll all have common variance s squared, which may not be 1. And look at their sum. As we just saw, the law of their sum is a normal of mean 0 and variance n s squared. So we're going to renormalize this sum And as we saw, if we want to stabilize the variance, we should probably normalize it by bn equal to square root of n. But let's be more general for the moment. Using the same kind of calculation we did on the first page, let's compute the CDF of the renormalized sum, Sn over Bn. Bn is, of course, non-negative, and so this can be written as the probability that Sn is less than or equal to Bn times t, which is the integral of the Gaussian density, and the appropriate Gaussian density is the one of variance ns squared. Now, we'd like to write this as the CDF of a random variable, and that means we need to have just a t here instead of a bn times t, so that suggests that we do the following change of variables. X should be chosen to be bn times u, our new parameter. That means that dx is bn times du, and after we successfully do that change of variables, this will become the integral up to t, and substituting in u is equal to x over bn and simplifying, what we'll get inside here is 1 over the square root of 2 pi n over bn squared, s squared, e to the minus u squared over 2n over bn squared, s squared, du. In other words, this is the CDF of a random variable z at t, where that random variable is a normal of mean 0 and variance n over bn squared times s squared. So, as we noted, in order to stabilize this, we need to let bn squared grow linearly with n. And so what we've shown is that under these conditions above, given an IID sequence of normal random variables of mean 0 and variance s squared, if I take the law of this renormalized sum, Sn over the square root of n, that is a normal of mean 0 and variance s squared for any n. More generally, I can allow the mean to be non-zero as well, and this leads the way to understanding how to put the mean and variance rescalings together. If I take a sequence of independent and identically distributed normals of mean alpha and variance s squared, then the law of Sn, the sum, minus n times alpha, which is the expected value of that sum, divided by the square root of n times s, the standard deviation, will constantly equal the standard normal law for all n. And just to note, another way to write this same thing here is what we've done is to take Sn, subtract off the mean of Sn, and divide by the variance of Sn. So there's our embryonic central limit theorem. If I take any normal random variable and take independent copies of it and take their sum, then standardizing the sum this way gives me a standard normal for any finite sum. And so, of course, if I now take the limit as n goes to infinity, in the limit, this law converges along this constant sequence to this measure. We're now going to head into understanding the generalization of the law of large numbers about what happens to the mean and the central limit theorem. The point being that this statement in the limit does not require the SNs to be normal. It only requires them to be independent.